Hello everyone, my name is Mustakimur Rahman from Florida State University. Today I will present coin attacks on insecurity of Enclave Untrusted interfaces in SGX. This research collaborated with my advisor Professor Wang and Yueqiang Cheng from Baidu Security. I am going to start with some background on Intel SGX. Intel SGX is a hardware support for trusted execution environment, also known as TEE. The TEE concept basically separates a system into two parts, trusted enclave and untrusted system. Intel SGX handles memory isolation of trusted enclave so that the untrusted system could not manipulate the enclave behavior directly. This gives integrity and confidentiality support to the enclave. So according to Intel SGX threat model, other than enclave and the CPU, everything else is untrusted. A developer could decide a part of the program to be enclave using Intel SGX SDK, which generates an API to build the communication channel between the unsafe application and the enclave. Now, our concern is how could unsafe application indirectly manipulate the enclave behavior to trigger a vulnerability inside the enclave? Because if enclave has an exploitable vulnerability, that will destroy the entire trust model. So we study the enclave interface that controls the interaction between unsafe application and trusted enclave. This is a perfect attack surface for malicious user to exploit an enclave vulnerability. We found 4 possible attack models that could indirectly manipulate the enclave behavior. First, as the dependent threads are unsafe, so the concurrent threads would allow an attacker to misuse race condition based bugs inside the enclave. Second, if there is a control flow hijack in the host application, that could be used to call enclave interface function in unexpected order, which in absence of developers consideration could be significant. Next, both the call to enclave and call from enclave can bring malicious input data into the enclave when the memory is still isolated. Such inputs could manipulate the enclave execution in some degree. Finally, there is another threat when the enclave is queried outside. The execution at that point could be hijacked to call another enclave function before the last call returns to the enclave. We call the 4 attack models combinedly the coin attacks, that is concurrency, order, input manipulation, and nested calls. Except the 4th model, we have developed a framework to simulate the other 3 models in an attempt to detect enclave vulnerabilities on the presence of coin attacks. We are studying the 4th model in a broader extension and left it for the future work. The first information an automatic vulnerability detector would need to simulate the coin attacks is the API information for the target program. Fortunately, we have enclave definition language or EDL file in the SGX enclave projects. The SGX SDK uses a tool called Azure 8R to automatically generate the interface based on that EDL file. This file consists of a trusted class where the list of equals, that is available enclave function to call from host application, and an untrusted class where the list of OCOs, that is host application functions, can be called by enclave are listed. Additionally, the function parameters are annotated with data flow direction and type information. Upon this API information available, we design an extensible framework for coin attacks. We call the framework extensible because we have a policy module where anyone can integrate a new security sensitive policy to detect new vulnerabilities. The other 2 modules are API parser and core modules. The API module collects API information using 2 different tools. The EDL parser parses the EDL file that we have mentioned earlier, and the bitcode parser digs deeper to extract memory layout of the complex data structures uses in the equal or OCOL function parameter. The core module is responsible to simulate the coin attacks. It also has two components. A QEMU parser emulates the enclave instructions in the arbitrary order of equals and hooks the OCL at the emulation. The symbolic engine can generate new seeds for symbolic variables based on their path constraints. With the help of API information, the controller takes the required function parameters, which are enclave input, as symbolic, and the symbolic engine replaces their value before equal and during OCL hook. Additionally, to simulate the concurrency thread, the instruction processor has two modes of operation. In single thread mode, equals are emulated sequentially from a single thread. In a multi-thread mode, every equal from a sequence gets its dedicated thread. The threads are controllable through the controller that allows a policy to manipulate the instruction processing. During the simulation, the policies could report comprehensive vulnerability reports. Here you can see an use after free vulnerability report that consists of information of how the event is triggered and related debug information. Based on the seed information, we replay those executions concretely to verify the report. In our artifact, we have applied 8 different policies that could be categorized into information like memory vulnerabilities and control flow hijack. In next few slides, I will discuss how we enforce those policies with case studies. We found 3 information leaks in 10 open source SGX projects. I will discuss one of them from embedded TLS SGX project that would leak entire enclave memory using the input manipulation attack model. In the function you are seeing, we highlight a loop that is constrained with an OCL return in line 9. You can see the return is only validated against equal less than 0, but the SSL out left is unsigned in, so the subtraction in line 15 could cause an integer overflow by the return value greater than SSL out left. So the attacker can control the loop and cause a denial of service inside enclave. But this is not interesting. In line 5, you will see a heap or buffer points to is also calculated based on SSL out left that is under attacker control. Moreover, the buffer is using in OCL in line 9 to send outside of the enclave. So an attacker can control the loop and also can points to any enclave heap location to leak sensitive data outside. Our policy is to detect these vulnerabilities starts with identifying an attacker control loop that is constrained data is symbolic. Once it is identified, the loop body is analyzed to see if there is any OCL and later checks if any of the OCL parameter is using as output and also tainted by symbolic data. The second policy I would like to share is an use after free vulnerability from SGX SQLite project. The vulnerability also available in SGX SDK library support. This case study also demonstrates the significance of the order and the concurrency attack model. In this code, there are 3 equal functions. Equal OpenDB accepts a string and allocate a SQLite object and assign it to a global reference pointer DB. Equal execute SQL accepts a query to execute with the allocated SQLite object, and equal close DB frees the allocated memory of SQLite tree. Now in SGX SQLite project, the developer assumes the equal will be in order that is OpenDB to execute SQL to close DB. But as those equal order could be manipulatable from unsafe application, we found that an equal order of OpenDB to close DB to execute SQL trigger and use after free. It is because the developer forgets to set the reference pointer DB to 0 after the free operation in SQLite 3 close function. It is also noticeable that if developers set the reference pointer to 0 in equal close DB, it also needs to be protected by spin locks. Otherwise, concurrency would still find out a way to exploit the same bug. The policy just keep track of memory allocation, deallocation, and verify memory during memory dereference time. But also to ensure concurrency case, the policy requests a pause to the other threads if the current thread hits a free request. The third policy is specifically interesting in TEE concept. We call it ineffectual condition. In the case study from SGX re-encrypt, there is a conditional statement in line 19. It compares a certificate expiration date against the timestamp. If we look closely, we would see that the timestamp is collected from unsafe environment using an OCall at line 13. Also, the certificate is extracted based on an equal input, that is the client ID. So in that condition, both sides are tainted towards symbolic data, which means an attacker could manipulate this control flow. What is more interesting here is that the condition is a validation check, and we could say it by analyzing the fall-through code where it only assigns an error code and return using an unconditional jump. In our policy, we check every conditional statement that are symbolic and verify if its fall-through basic block is error code generator. For this case study, an attacker could send a client ID and use its certificate, although the certificate might be expired by passing the validation check. We have implemented 4 other policies that are similarly serious like that we mentioned earlier. Null pointer dereference is not as interesting as them, but I would like to share it because we saw a common pattern of it in our evaluated open source SGX projects. In this code, we are showing the API function SGX_SGX encrypt file defined by SGX SDK, which accepts a common structure from unsafe application. The in encrypt message out supposed to use to output a computed buffer from Enclave. However, if the unsafe application sends a null pointer instead, the API function will not allocate any Enclave memory for in encrypt message out. Now, in the developer return with Enclave function SGX encrypt file, we can see developer uses a memcopy to copy the computed output buffer to the message out, which is basically the null pointer because of encrypted message out. While we study the SGX SDK, we found they use memcopy_s instead of memcopy to avoid this situation. But most open source developers either did not know it or ignore it and cause a common pattern of null pointer dereference. We have evaluated 10 open source SGX projects such as embedded TLS SGX, Intel SGX SSL, SGX SQLite, etc. of different levels of complexity. We detected 52 vulnerabilities in total. Here is a distribution of the reported vulnerabilities across different policies. There are 8 information leaks, 9 control flow hijacks, and 35 memory vulnerabilities. One of the interesting projects is Intel XGX SSL. It is a port of OpenSSL by official Intel XGX team. Our system reported total 5 vulnerabilities in this project, 3 of which are detected as ineffective condition. In a different perspective, here is a distribution of the reported vulnerabilities based on different attack models. 78% of the vulnerabilities are because of input manipulation. Call permutation and concurrent calls contributes to detect memory vulnerabilities such as use after free and double free that are closely related to execution status. There are 13 vulnerabilities that are null pointer dereference, which we have already shown uses a common mistakes by the developers. We built the artifact using Clang LLVM compiler version 9, Triton symbolic engine, and QEMU emulator. We evaluated the open source project built in Ubuntu OS with Intel XGX SDK version 2.5. We used an Intel Core i7 32GB machine and allocated 30 hours for each project simulation. We saw multi-thread mode of emulation is 6.5 times slower than single thread mode of emulation. Also, some of the projects finish its simulation within 4 hours. There are few limitations in our artifact we found during evaluation. For example, QEMU did not recognize some of the new instructions such as Intel CTISA. There are also limitations from Triton that could not analyze ISA such as Intel AES NI because they are too complicated to handle by a symbolic engine. Also, we left in nested calls as feature work because we are planning to study it in broader extension. In conclusion, in this research, we introduced the coin attacks, how unsafe application could trigger enclave vulnerability indirectly. It consists of concurrency, order, input, and nested calls attack models. We proposed the design of an extensible framework targeting coin attacks. We implemented the design with 8 detection policies, which could be categorized into information leaks, memory vulnerabilities, and control flow hijack. We evaluated 10 open source SGX projects from GitHub and found 52 vulnerabilities. Our artifact has been evaluated and open source in the following link. Check it out from there and share if you like it. Thank you.